Today we're going to be talking about testing microservices with consumer-driven contracts. So essentially we're going to look at how we can improve the way we can test microservices. So before I get started with this, I just want to kind of explain that microservices testing is a lot harder than what we initially believe. I think with microservices, we start with these independent, autonomous projects that are quite small, easy to maintain. They tend to be modeled around a single business functionality, and they're independently testable and deployable, releasable to production. So it must be therefore easier to test microservices. If you take something like a monolith, you can provision an instance of it on your local workstation. You can then fire some tests against that monolith, and when those tests go green, you can release the whole monolith to production pretty confidently, in a sense that you've not broken anything. Although the monolith is bigger than the microservices are distributed. And the fact that the microservices are a distributed system with message passing between microservices is what makes it so challenging to test. So if you're familiar with kind of trying to end-to-end test microservices and ending up with kind of slow and flaky, unreliable builds, or testing microservices independently, only to discover that when you ship your microservice to production or an end-to-end test environment, it doesn't work with the microservices that depend on it, then you'll know the sorts of problems that I'm talking about. So consumer-driven contract testing is what I'm going to be talking about throughout most of this presentation. In a nutshell, it's a way to mitigate the microservices testing problem by testing against contracts. So we have shared contracts that we run the tests of our microservices against to try and guarantee that they will function together when we deploy them together. So about me, my name's Andrew Morgan. I'm British, so I'm from England originally. I currently work in the Netherlands, so I'm an independent consultant who specializes in microservices, continuous delivery. I've been with ING in the Netherlands now for around a year. I mainly work on microservices architecture and development. I'm also a Pluralsight author, so I have a couple of Pluralsight courses online that are available to watch. And I also write news for InfoQ, so I take interest in architecture and design, so I write for the architecture and design queue. So on the agenda, the first thing I want to talk about is some of the microservices testing challenges, because I think it's important to try and understand what the context is that's led us to adopt continuous consumer-driven contract testing. Once I've done that, we'll then give an overview of consumer-driven contract testing. We'll learn about how we can use it to mitigate some of the problems in the previous section. We'll then follow through CDC using the framework. And although this is kind of a Java framework that I'll be using in the example, it's just a short section. And because it's such a gnarly subject, I think it's still useful to see some code examples in order to understand more easily how we actually go about CDC. And finally, I'm going to cover some advanced consumer-driven contract testing concepts. I say advanced, it tends to be the stuff that I don't have time to talk about during the presentation. So there'll be a short section on messaging, creating contracts using regular expressions, and also a contract repository. So I'm sure we all know what microservices are. They're not particularly new anymore. We've all been working with them for a number of years, but it's good to set the context so we're all on the same page. With microservices, we have many different services, each of which is modeled around a single business functionality. And those services as a whole form a single application. So in the example here, we have an account service, a reward service, a payment service, and a loan service. These are all independent projects, maybe with separate teams working on them. They can all be tested in isolation. They can all be released independently to an environment. With microservices, though, we often have some form of communication between them. So the kind of example that we're all the most familiar with is HTTP, synchronous communication between microservices. And we also have message-driven communication. Maybe we have more of an event-driven architecture. But the point is that microservices, despite being autonomous, have some form of coupling through message passing. And that's the core problem that we have to address. If you do want to know more about building microservices, I would recommend this book by Sam Newman. It's the first book I read on microservices, and it's a really useful way to get up to speed with the topic. Okay, So say I have a payment service and I want to work on it independently. So I would clone my payment service project. I would make some changes to it, update my tests and make sure my build goes green. Once I've done that, in theory, I should then be able to ship my payment service to production with my latest changes. The problem arises when my payment service is depended on by another service. So we'll say it provides a HTTP API that my booking service depends on. Now, I can't necessarily deploy my payment service after running only the test for the payment service, because I need to know that my payment service and the changes that I've made to it will not cause it to cease to function with the booking service. So both my payment service and my booking service need to still work together when I change only my payment service. And if you think about the way these sorts of architectures go, we can often have many dependencies between many different microservices. Now, I'm not necessarily saying it's the best thing to do is to have this spider web of dependencies between services, but it's not unreasonable to say that it's a problem that we're going to run into at some point. So the first way to kind of mitigate this testing problem, where we need to guarantee that our one change to a service won't break the other services that depend on it, is to end-to-end test. So with end-to-end testing, we have some automated tests that may live in an independent project, and they would then drive interaction with the application through a browser, through a user interface of some sort, just like they're the real user of the application. Behind the scenes, we have all our microservices deployed together, again, just like they would be deployed together in production. So this is great in the sense that we test and build everything together like a monolith, which gives us the certainty that everything works together. Of course, although it looks like a good idea at first, it's not, and there's numerous reasons for this. The first reason is build time. So when I end-to-end test a microservice, I have to run the build for my microservice on a CI server. I then have to test it, build it into a package, and deploy it to an end-to-end test environment. I then need to run all my end-to-end tests, which might be quite slow if they drive the interaction through a user interface like a browser. The debuggability is also something that we can run into as a problem, because if you have an end-to-end test that drives the application through a UI, when the test assertion fails, we would just see something like a button doesn't appear on a web page, we see an error pop up, something like that. But identifying the root cause is often a lot more difficult than that, because we do something in the UI, we trigger many network hops in the backend, and one of those network hops is the one that will have failed. So we need to go through our aggregated logs of many different services and think about how we can trace and diagnose exactly what caused our test to fail. It's just not as simple as running a unit test on our local machine, which goes red and gives us a stack trace. We're also spending a lot more money on infrastructure, because if we're having to end-to-end test our microservices all the time, we need to have this end-to-end test environment where we deploy them all to. Maybe we want to run many end-to-end tests in parallel, so we need more than one end-to-end test environment, which increases the cost some more. It is easier now in the sense that we have the cloud, we can provision infrastructure cheaply, we can only have it up for the time that we need it, but fundamentally it still costs money, and it is free to do this kind of stuff on your local workstation. From an operational point of view, end-to-end testing is also a lot more complicated, because now somebody's got to worry about provisioning and configuring your end-to-end test environments. They've got to worry about setting up things like monitoring, setting up logging, managing it if it goes down, all these sorts of problems you have in maintaining these environments. This is my personal, this is the one that I dislike the most, which is test flakiness. The whole point of automated testing is that it gives you fast and reliable feedback that can give you the confidence you need to deploy your application to production. If you're running a 4.5-hour build through something like Selenium to tell you whether you can release your application to production, and that build fails for a different time because the tests are flaky, then that's not great. So these kind of end-to-end tests that kind of work their way through a user interface and through the system are a lot harder to make reliable. And really, there's an umbrella term for all of these sorts of problems, and that is the distributed monolith. So what we're doing here is we're building and testing our microservices as if they are a monolith. And by doing that, what we're doing is taking the disadvantages of a monolith and the disadvantages of the microservices, the distributed system, and fudging them together into one of the most common microservices anti-patterns. So we really don't want to be building and testing our microservices like a monolith like this, because we're not getting any of the benefits of microservices. So we can't end-to-end test because it's slow, flaky, and reliable. We're creating a distributed monolith. So the alternative might be to really just test a microservice on its own and then ship it to production without end-to-end testing. So maybe we set up some automated tests, which this time run against our microservice on its own. So our microservice is spun up independently, and we treat it as a black box with some tests that maybe make API requests against it, assert certain things are written to the database, that kind of thing. When our microservice then needs to call out to another service, we can then mock or simulate that other service using the mocking framework. So in Java land, we have Mockito, which is probably the most popular Java mocking framework. And we also have tools like WireMock, which are HTTP simulators for APIs. But the concept is we only have to run the build for our individual microservice on its own to verify that it functions. And we just simply simulate all of its dependencies to avoid end-to-end testing. So now we've got the kind of fast feedback and the independence that we want from our microservices. Only it's not really that simple. The first problem with this, if it's not obvious, is false positives. So there's still a manual process of creating all the mocks of your dependent microservices. And you have to make sure that you don't make a mistake when you do that. If I create a mock for an endpoint/user without an S, and the real endpoint is /users, my test will go green because they called /user without the S. But then when I deploy to production or an end-to-end test environment, everything will just kind of fail because I was calling the wrong endpoint and my mock was simulating the wrong endpoint. If we do manage to keep on top of this manual process of keeping all our mocks up to date and reliable, we then have to worry about them being stale, because microservices tend to be quite evolutionary. We change them over time, we version APIs, we do all sorts of make all sorts of changes quite frequently. And if we do that, we need to make sure that those changes aren't going to break communication with the existing dependency. So how do we make sure that our mocks are always reflective of the real service, even though those services change frequently over time? And the umbrella term for this is just maintainability. It's just difficult to maintain these mocks of all your different microservices in a way that makes them reliable enough for you to confidently test independently and ship to production. So kind of a naive implementation of how we can mitigate these two problems is to fudge the two ways of testing together into a continuous delivery pipeline. So we hope that the disadvantages of both cancel each other out, and we take the advantages of both. So we start by testing an individual microservice. So the test of the individual microservice spins it up on its own and mocks everything that it depends on. Once we've done that, we can deploy that microservice to a stage environment. So we have to wait for it to build, to deploy. We can then, once deployed, end-to-end test our microservices. So our end-to-end test environment would typically be the same as production, plus only the microservice that we've changed. And once we've run our end-to-end tests and they go green, our microservice is releasable to production. Only the first step is not as useful as we would like, because we get a lot of false positives from all the mocking that we set up ourselves manually. So we're getting through what would be the fastest feedback. When we get through it, we go to the end-to-end testing, but the end-to-end testing is a lot slower. It can be a little bit flaky. So we're not really getting the good feedback that we need if we take this strategy. And in fact, the idea of releasing phase off into the distance is something we think will never happen. And this isn't really a good situation to be in, because what we're trying to achieve is features that we can develop as quickly as possible, that we can ship to production as frequently as possible, and we can do so in a way that doesn't introduce any regressions. So this kind of distributed monolith architecture and unreliable mocking and stubbing isn't really a way to quickly and to have these independently testable, deployable, releasable microservices. So I'm now going to talk about consumer-driven contract testing, which is essentially a testing technique for microservices to mitigate many of these problems. Consumer-driven contract testing fills a microservices testing gap. So if we take the mocking and the stubbing and we take the end-to-end testing, CDC kind of sits in the middle as the answer to both. It's a technique in which we continually test our microservices against contracts. So we have shared contracts representing interactions between services, and the builds for the services on both sides of that interaction are continuously tested against those contracts. They just run as part of your ordinary unit tests. It's also a technique in which the consumers drive the implementations of providers. Now, this will become clearer in a future slide, but the idea is that rather than starting with a provider-first implementation of an API, you create a failing test on the consumer side, which drives the API design of the provider. And finally, the kind of core goal of CDC is independently testable and releasable microservices, because that's the goal of microservices. If a service can't be changed independently and released independently, we're not really taking away any of the benefits. So a CDC test architecture overview would involve a consumer and a provider. So the consumer would be a consumer of an API and the provider would be a provider of the API. What we need to do is guarantee that the communication between these two services via the API will work as expected. So I want to I want to be able to release my consumer or my provider and know that I'm not going to break this communication. With CDC, we achieve this with contracts. So we create a contract to represent the interaction between these two services. We then have contract tests that run on the consumer side. So as part of the consumer's builds alongside its contract tests, alongside its units tests, it will have contract tests which also run. And the independent builds for the provider will use that same shared contract and it will run its contract verification tests. So we have a shared contract that's tested against on both sides of the interaction. A contract itself is an agreed interaction between microservices. So see it as a test scenario, a request and response between an API that must be made in order to make a test pass. It's something that's continuously tested. So we run our contract tests every build for our provider and our consumer. And in doing so, we help guarantee that the two services will always function together. It's no specific protocol too, so I talk mainly about HTTP in this presentation, but that's just because it's kind of what we're all the most familiar with. But anything that represents an interaction between services, in theory, would work with CDC. It's also not the same as stubbing. So a lot of people say, well, you're creating a contract, you're generating a stub from that contract. How is this different to manually creating my stub with something like Wiremark? It's very different, and the reason why is you have verification on the provider side of CDC. So just stubbing is kind of half CDC, where you only verify the interaction on one side. With CDC, you verify the interaction on both sides. And it's definitely not API documentation. API documentation is a description of an API. An API documentation is not continuously tested, and there's no guarantee that the underlying code implementation matches that API documentation. So let's say we have a test scenario, an interaction, and this interaction is what would belong in a contract. So we have one here, should return no flights between London and Paris. We'll say that there's been a no-deal Brexit, we can't fly to Paris, and we've got no access to cheese and wine anymore. We have a required request, a GET request to slash flights from London to Paris. And we have a given response, which is a 200 response with an empty array. So we want no flights to be returned, and our contract expects a call to the flights API, and it will give a response of an empty array. So on the consumer side of the interaction, we would start with our automated tests. We would run them against our consuming microservice. And eventually, our consuming microservice would make the API call that we just saw in the previous screen. When it makes that call, that's the point in which we need to create our contract. Our contract creates the interaction that our test depends on in order to be able to pass. And once that contract is complete, we can use it to generate a stub. And that stub will be spun up as part of this automated test, and it will allow our automated tests to go green. So rather than programmatically creating a stub, we just define a contract and then use the CDC framework to generate a stub for us. Now, on the provider side, we do kind of the opposite, do everything the opposite way around, because we already have a contract that we define to make our consumer side tests pass. We can then simply take that predefined contract and then use it to generate contract verification tests. Again, this is something that the CDC framework would do for us. And what the contract verification tests do is make the request in the contract, so our call to /flights against a providing microservice, and they will assert that the response that the providing microservice gives is exactly the same as a response in the contract. So we have on one side stubbing, where we call our stub and we get the response in the contract, and we have on the other side verification, where we make the request in the contract and assert that the response we get is the same as a response in the contract. So the kind of benefits of this approach: fast and reliable feedback, because we have the speed and reliability of, testing microservices independently without end-to-end testing. We have the speed of mocking and stubbing, but we also have close to the reliability of end-to-end testing in the sense that we know all our stubs, all our mocks are going to be representative of the real service. If I want to make a change to, say, the provider, then my contract test will run and tell me whether that change is a breaking change. We also don't need end-to-end testing now anywhere near as much as we did before. I'm not saying to never ever end-to-end test, but what I am saying is we don't need to do it as much. So we're going to be spending less money on infrastructure. We're also creating an API that delivers exactly what's required, because we're driving the implementation from the outside in, starting with a business requirement. And rather than some team which own the provider service saying, here's our API, you guys consume it, you're starting with a failing test that's required. You start with a failing test, and that failing test can drive the implementation of the API. In terms of dependency hell, it's also a way to reason about that a lot better. So with microservices, we have lots of dependencies between services that we can often find difficult to understand. Now we have an interaction captured in a contract, every single interaction between every single microservice. So you can infer how all the microservices depend on each other, and you can also be confident that you're not going to break anything when you make a breaking change to the API, because the contract test will fail. We no longer have stale stubs, again, this point, which is that we make a change to our provider, that provider change is a breaking change, the contract tests fail. So we have continuous testing on both sides of the interaction that make it impossible for our contracts or our stubs to become stale. And finally, it's easy to work in parallel, because now we have a shared contract. We can have somebody work on one side, somebody work on the other side, and when they're both finished, we can be relatively confident that the two services will function together. Okay, so now I'm going to walk through the CDC workflow using the framework Spring Cloud Contract. If you're not a Java person and you're not a Spring person, it's not necessarily, this is still probably quite useful, because it's a gnarly subject to get your head around, and the concepts kind of apply regardless of what language or stack you work with. So the two CDC frameworks that I'm the most familiar with are Spring Cloud Contract and Pact. Spring Cloud Contract fits very nicely into kind of the Java Spring ecosystem if you work with that stack. And Pact tends to be more of a cross-platform approach to CDC. So if you have a more kind of polyglot architecture, Pact can be maybe a bit more useful. And I know now there's some interoperability between the two. I'm not exactly sure where that's at, but I think Spring Cloud Contract also understands Pact contracts. Okay, so as I say, Spring Cloud Contracts, it's not necessarily the best framework. It's just the one that I've decided to use for this example. So Spring Cloud Contracts is a JVM-based CDC framework. It integrates very nicely with kind of the Spring Boot stack, if you're familiar with that. So you have the whole concept of convention over configuration or default configurations, where you don't really have to do much to get everything up and running, just add a dependency and a few lines of config. It also comes with a Groovy-based contract definition language. So if you're not familiar with Groovy, I wouldn't worry about this too much. It's something that you can pretty much understand straight away when looking at it. And it supports message-driven and HTTP-driven interactions. So both the kind of the synchronous and the asynchronous ways of doing CDC. So we're going to start by building a feature, and we'll go through the CDC workflow step by step for that feature. So we'll start with a unit test which runs against a credit card application service, which calls out to a credit score service. So our unit test will apply for a credit card. Our credit card service will accept or reject the application for that credit card. And our credit score service will calculate the credit score for the user applying for the credit card. If the score's, say, a high score, then we'll accept the credit card application. If the score's a low score, we would reject the credit card application. So here are the steps. There's 6 of them, and we'll go through them one by one. We start with a failing test. CDC is a test-driven approach to developing microservices. So our example here, if you're not a Java person, it doesn't matter too much. We have a test which makes a request to our credit card application service with some JSON, requesting to apply for a gold card. And we have a test assertion that asserts that the credit card request was granted. So we have our JUnit test that we execute, and then we can then start to build our credit card application service in order to make our test pass. Eventually, we'll have hit a certain point where we've implemented a lot of our credit card application service, but we have a failing network call to the credit score service because the credit score service doesn't exist anymore. So our test will fail when it tries to cross the network boundary to something that does not exist. And that's the point where we define our contract. Our contract is used to make our test pass. So the contract definition language in Groovy is the request made by our service under test to our credit score service. So we're calling a credit scores endpoint with the citizen number, very simple example. And we have a response in our contract, which is a response our test requires in order to be able to pass. Once you've generated our contract, we can then build stubs from our contract. So we take our contract and we run it through our CDC tool. This is the same concept for all. And we come out with a stub jar, which represents which is a stub that we've generated from our contract. The stub itself runs in YMOC. So if you're not familiar with YMOC, it's a HTTP simulator for APIs. We then need to make our test pass, and we can do that by using the stub in our test. So we take our credit card application service tests, we can configure it with the stub runner, and it will mean that when we run our test, we will download our stubs, we'll boot YMOC, and we'll import our stubs into YMOC. It's just a simple annotation at the top of your test. Once we've done that, we can go from our failing credit score test to a passing one, because we have a YMOC stub that our test will call out to instead of the real credit score API. Our test will now pass because we've generated our stub from our contract. Okay, so we've started with a failing test. That failing test has made a network hop. We have that network hop and we've used that to create a contract. Once we've created our contract, we've generated stubs from our contract, and we've used those stubs in order to make our test pass. That's everything done on the consumer side. We then need to switch to the provider side to make sure that the provider also complies with the same contract. So we build our verification tests. To do this, we take our contract, we run it through our CDC tool, and we get verification tests. All the verification tests do is make the request in the contract, so the call to the credit scores API, and then they assert that the response that we get is the same as the response in the contract. We don't have to write these tests ourselves, they're generated automatically for us using the CDC tool. And finally, we need to make these tests pass, and these tests are what will drive the implementation of the provider. So we have our contract verification tests, which fail to begin with as we've yet to implement the endpoint, and then we just simply implement the credit score service until our contract verification tests pass. And once we've done this, we've got CDC tests on both sides of the interaction that will give us a lot of confidence in deploying these two services, in the sense that we think they will work together because we have these contract tests. An interesting quote is one from Marcin, one of the core contributors to Spring Cloud Contract. And he says, consumer-driven contracts are like TDD applied at the API level. And I think that's something really interesting to think about, because we're taking all the benefits of TDD. We start with a functional requirement, and from the outside in, we start to implement things by making tests pass. Eventually, we hit the network, and why not apply the same concepts of TDD over the network? We then have every single interaction between every single service captured in contract tests. So we have the regression testing, we have the regression that you get with TDD for free. If I make a breaking change to my API, then my contract test will fail. So it becomes very, very hard to introduce regressions. So finally, I'm going to talk about more advanced consumer-driven contract concepts. And they're not necessarily advanced, it's just the stuff that I haven't had time to get to during this presentation. So the first question people tend to ask me is, does this work with exact comparisons? And what I mean by that is, I've given a very specific request that gives a very specific response. But sometimes we might have more dynamic data. For example, a UUID that we send in the request, a timestamp, something else. And to get around this, these frameworks are actually quite flexible. We can introduce things like regular expressions. We can introduce JSON matching, which doesn't care about white spacing or the ordering of JSON fields. So you can be very flexible in defining your contracts, and you can allow a wide varying or dynamic, you can allow lots of different requests to be matched by the same contract. The other question tends to be around messaging. So with message-driven communication between services, or maybe more event-driven communication, we have producers and consumers of messages. Between them, we have a broker. So our producer will fire a message, and then all it will care about is that the broker is able to consume that message. It doesn't know what happens to the message afterwards, and it shouldn't care. On the consumer side, we have the kind of opposite way of thinking. We only consume messages from a broker. We don't really have any direct interaction with the producer of the messages. And this this message-driven interaction creates an inherent decoupling between services, because they no longer talk to each other directly. And because they're decoupled through messaging, you might often think that we don't need to adopt CDC. I would actually say that the use case for CDC here is greater than it is for synchronous communication. The first point is that message schemas and queues are shared. So if I publish to a topic called, the example I used before, a topic called user, and I consume from a topic called users with an S, then I'm going to successfully be publishing my messages, and technically I'll be successfully consuming from the users topic. It just happens that the two got mixed up. The same applies to publishing things like JSON. If I publish JSON in one schema, if I use schema to publish JSON, and then when I unmarshal that JSON, I expect a different schema, then I would get some sort of exception with that too. And once you think about these sorts of things, how these sorts of things can go wrong, we then start to think about how difficult it is to debug them. The example I gave with producing a message that gets consumed from a different topic is a really good one, because it doesn't result in any kind of stack traces in your logs. Your message will be successfully produced, and your messages will be successfully consumed if they were released into the right topic. So if we can avoid going to kind of an end-to-end test environment where we have to trace through lots of different logs and figure out why messages that we publish and consume aren't doing what we expect, we can try and avoid doing that altogether by doing CDC. The final question is, where do we store the contracts? Because I've talked a lot about creating contracts and building tests around them, but not actually talked about where the contracts live. With the Spring Cloud contract example I gave before, the contract lives in the provider, a contract directory in the provider project. So when you run the contract test for the provider, the file is local in the project, and it's simple enough for those to execute. That same file will then be published to a repository, say Nexus, Artifactory, whatever you want to use. And then the consumer tests will pull the contract from that repository and run against that contract. Another interesting way, though, of doing this is using something like Pat's Broker. Pat's Broker is a CDC-specific repository. So with Pat Broker, we upload what they call packs, or our CDC contracts, and each of them is continuously tested against. So we can see a list of contracts when the pat was last published, whether we're green or red, that kind of stuff. So having a dedicated tool to do this is also something that can be quite useful. As well as that, Pat Broker allows you to do some interesting things. We have interactions between all our services, so we can infer what the dependencies are between all those services from those interactions. So here's just an example of a dependency graph that's been worked out for us based on contracts. So kind of the conclusion is to not build and test microservices like a monolith. If you're doing that, you have a distributed monolith, and you're taking all the disadvantages of microservices, the distributed system, and the disadvantages of monolith, the huge application that we have to build and test together as a whole every time. If you really want these independently testable, independently deployable and releasable microservices, then look at something like CDC, because it can help promote the independence of your microservices. And if you want to adopt CDC, you can leverage frameworks like Spring Cloud Contract and Pack to do this. So if you're, please give us some feedback. So you can rate the session in the O'Reilly Events app, and you can also rate it on the conference webpage. We always value feedback. And I think I have a little bit of time to take any questions if anyone has any to ask me. Sure. Hi. We've got a mic for you. Sorry.
Thank you. Yeah. This is much easier.
Yeah.
I was wondering if the CDC strategy can also apply to external services, whether that's a third party or just a microservice that you don't have control over, so you're not able to write those contract tests.
Yeah, so the question was, does CDC apply when you deal with external services that you don't have control over? The short answer is no, because you need both sides of the interaction to be on board with CDC. So if you define a contract, the owner of that external service then needs to include that contract in the build of their service and run contract tests. So if it's owned by a third party and you can't get them to create contract tests for the contract, then it's not going to work. Any of us? Sure. The question was any framework for C# or .NET. So I think I might be wrong. Pact supports C# and .NET. So I think the goal of Pact is to support pretty much as many languages as possible. It's a polyglot CDC solution. Yeah.
So I see how this works really well, but you have kind of peer function, like the output of it.
So for the cases where you need some state inside the microservice to be in a certain way for the contract to work, those tools also support that, like creating some context in the microservice?
So the question is, if the microservice you are simulating has some state, and you need to simulate that in CDC. So I think CDC is generally supposed to be more about, do I make a request to a valid endpoint? When I make that request, am I am I not making a spelling mistake in the query parameters? Is the schema of my JSON correct? That sort of thing. It's not necessarily for simulating stateful interactions. So I would edge more towards end-to-end testing if I really wanted to do that.
Just kind of to add on to that question then, does that mean that CDC is better for doing syntactical verification as opposed to semantic verification of the API endpoints?
So the question was, is CDC better for syntactical verification rather than semantic verification? I would say on a whole, it's probably better for syntactical verification, yes.
Hi.
Hi.
What about certain cases where there are, some rate limits imposed by the provider? In certain cases, can CDC help out?
So the question was, if there's a rate limit imposed by the provider, is there a situation in which CDC would help with that?
Yeah.
Yeah. So say the provider hits their rate limit and they return something like a 40, I don't know what the status code would be, 403 or something like that. And then you can create a contract that simulates that. So you can create a contract which takes an expected request, and the expected response would be that you have exceeded your rate limit response. So it's possible to simulate that with CDC too.
If the provider needs to change the contract,
Mhm.
and how does the consumer knows about the change?
So the question was, if the provider needs to change the contract, how does the consumer know about the change? The provider wouldn't change the contract. The contract is defined by the consumer. So what the provider can do is change its API. when they change the API, because the contract has not been modified, the contract test would fail if you make a breaking change. So if you get this failing build because you've changed your API because the contract tests fail, you would then do something like version the API or make a different change. So you always leave everything backwards compatible with the consumer that depends on that contract. Cool. Okay, thank you.